did
For the
before.
last two classes.
Yeah.
So do we start the lab this week?
Let's do it next week. It shouldn't. Yeah.
Are we going to continue using VAST? Let's go back to
No. Back to MATLAB. Computational chemistry ideally should be after this course.
Oh,
But
so it should be like quantum 1 fall, quantum 2 spring.
yes.
And then that's never gonna happen again.
Well, where it's on a scheduled basis.
No, where you have back-to-back quantum classes. Right?
I don't know. I feel they probably have to offer quantum 1 more often than quantum 2 since there's a PChem requirement.
No, but when they go this fall, there's no longer requirements.
No requirements?
I don't think there is a, like, mandatory, you have to take these classes. Is that true, Dimitri?
You'd have to do your process.
You need to repeat the question.
In this upcoming fall, with all their departmental changes in the policy, they don't have, like, classes that you must take before you graduate.
There was no votes yet, but
Oh, okay.
changes are going to be made. If oil prices will not go up, then any graded course that doesn't accumulate minimum five attendance will be dismissed.
So, pretty much all PChem classes.
If oil prices don't go up. I just got it. That's funny.
Oh,
He didn't concentrate on that one.
if oil prices go up, then one can teach a class for one student.
Right, of course.
Then cost efficiency is not the question.
I think we have to change some personnel before that even matters, though. Even when oil prices were high and the state was winning tons of money from oil prices, they still said, oh, sweet, there was surplus, don't spend anything. But there's better than now. Let's say that.
Do we have, who are we missing today?
Sam and Aaron,
Aaron,
and that's it.
How do I politely remind them?
Just class question mark, question mark, question mark? On the subject.
So you
Question
wouldn't,
mark with
on my
some
place, you wouldn't
explanation.
say like, dear younger colleagues, would you consider comfortable attending our next meeting which has just started?
No.
That's
next
no.
week just.
Because they're not your colleagues.
And class question mark is even better because it makes them wonder.
Oh, shoot.
Like, oh, is he mad? Is he angry? Is he just reminding us? They don't know. So they can run.
So
I'm sure Sam, either the bus is late or something.
It's just strategy.
No, Aaron's not, he's going from Dunbar.
Oh, yeah. No, no.
is Aaron here in the city?
I don't know.
Because
He's not my grad student.
Oh,
but you can become friends and know more about each other.
That's true.
He wasn't at the talk yesterday, but I don't know if he...
Yeah, he was. He didn't return from the weekend yesterday.
Oh. That would be nice.
But he.
But he worked on last Monday.
Okay.
holiday.
Since we are not
Running out of time.
not yet, but you better go on and we'll just share recordings with the guys if they do not show up. I'll collect. So, what you are reminding me to do is to collect homeworks.
How'd you fit that on one page?
Number whatever 2.
It's probably not as complete as it should be.
So let's make a little, I wouldn't call it exam, but session of mini presentations so that I sit and listen and relax and you present something. And let's practice democracy. So I'm going to distribute a list of possible presentations that you would select what you are feeling comfortable to present. And in a week from now, welcome. So in a week from now, you do like 4 or 5 minutes presentations on the practical applications of the materials that we covered in the class. So it shouldn't be something heavy, it should be pure pleasure for you. So, and then I'm going to distribute, I don't remember, like 4, 5, probably 4 pieces of handouts, all going out of this meeting, like V handouts on Russel-Sounders terms. So we are moving on from boring pure theory, maybe for some of you it's not boring, to practical applications. So it will be more developing scientific intuition and doing very simple calculations, just nomenclature and intuitive understanding of this nomenclature for practical systems with large values of angular momentum. So we are going to cover 4 subjects scientifically. The last one will be boron atom angular momentum. The second last will be a quick recall of Hans rules. The third last will be microstates table, and the first will be Russel-Sounders terms symbols. So if you were taking the inorganic classes in inorganic chemistry, then you probably would consider what we are doing right now as childish stuff, very primitive and boring. But if you missed this part of education, then you would enjoy it and see the connection between quantum theory and practical applications. Can I make a little inquiry about your experience with inorganic? Did you ever take the inorganic classes? Raise hands who took it ever. Raise hands who never took inorganic.
I've taken
organic
chemistry like 200 level.
Are we talking undergrad or graduate?
Whatever.
Oh,
So you were exposed to some level. Good, good. So let's make a fair trade. This is, well, I suggest I just distribute the list of questions. You look through them and you may develop your final decision within 2 days, and on Thursday you will tell what you would like to present on Tuesday. Okay? Because some people are quick thinkers and some need time to cook the ideas. Homework? Thank you. Here's the food for thought. Thank you.
I sent mine to you.
Oh, electronic.
Yeah.
Everyone
Oh, I
good?
didn't get one. Thank you.
And if you do not, we'll go through them, but if you do not find subject of your pleasure, you may suggest one. So the idea is that we find connections between your newly accumulated skills in addition of angular momentum and something from the practical applications of the systems where the angular momentum is not negligible and one should take care of it. So if you are not sure about applications, you still may select some purely abstract theoretical topic, but most of the suggestions are based on the subject that we will cover today and on Thursday. So it is nomenclature for angular momentum states for metal ions. And some of the applications are also for non-metals where spin is non-negligible, spin and angular momentum. So handout number 1 is a brief summary of what we're doing today, and it contains the definition of this Russel-Sounders term and summary of the rules to build the table of microstates and the summary of Hans rules that we may practice a little bit. One of the possible subjects for presentations next Tuesday, and I consider it as the easiest one, is to look for ground and lowest excited state of lanthanides ions. They are selected because so you may decide, okay, whoever need lanthanides, where do we see them? Like luminescent lamps do have them for light emitters. And if you deal, well, generally one needs angular momentum if one is dealing with metal ions. This is immediately necessity to use them. And your train of thought may go the following way, like, why should we go to so exotic materials if we do have transition metal ions? Like vanadium, titanium, iron. Well, if you would like to deal with transition metal ions, one immediately needs to take into account environment and crystal field splitting. And lanthanides are simpler in the aspect that the half-filled shells that contribute angular momentum are screened from environment, and they do not experience crystal field splitting. So although there is a larger number of electrons, in some aspect they are simpler. So if you are, of course, it would be not possible to cover it here in class, but if you are looking towards this lanthanide questions as possible subject of your presentations, here is the page from a textbook that briefly overviews the angular momentum states of lanthanide ions. And if you ever practice to find Russel-Sounders terms for a couple of lanthanides, you will be master of this subject, because there are really high values of angular momentum, and as you practice it by hand, you will never forget it. What else? Second opinion, standard text for quantum for chemists, Donald McQuarrie. Also on this Russel-Sounders symbols. And you do not need to read all these materials. It is a second opinion. If you do not trust me, you can trust the textbooks. It's more like entertainment. And I have prepared one more handout, but if you were exposed to inorganic, undergraduate inorganic, you probably do not need it because it overviews some examples from at the undergraduate level, which probably we will not overcome today. So, if we are dealing with closed-shell compounds, molecules, nanostructures, if the number of electrons is even, then most energetically favorable state is singlet, when we do not need to think about angular momentum at all. But if the number of electrons is odd for some shells, even for even number of electrons, if there are some half-filled shells in one of few ions in the compound, then sometimes the ground state and excited state of the compound is away from a singlet, and one needs to take it into account. For example, it's good to know what you are working with, and if you are doing computational modeling, then as some of you were taking computational class, one needs to explicitly request spin resolved calculation and have an idea what to look at. So, what do we do if we suspect that model that we deal with has non-zero angular momentum? So we exclude from consideration all closed shells and look only on the open shell. And then we are adding angular momentum, not at the high level theory as we did before, but intuitively. So as a first step, we assume that all spins of electrons do not interact with each other. And we can add all of them together. Then we assume that angular momentum of all electrons do not interact with orbital angular momentum, do not interact with each other, and we also add together angular momentum of all electrons. And then we assume that angular momentum of spin and orbital angular momentum also of all these electrons, again, do not interact with each other, and we add total angular momentum from spin and from orbital motion. So, since it is substantially multi-electron problem, there are several combinations of spin angular momentum and orbital angular momentum that can result in the same total angular momentum, and their magnetic and spectroscopic and energetical properties will be different. So one needs to keep track of these features. And this stuff is typically summarized in the so-called Russel-Sounders term. So this symbol characterizes the ground state of a system where angular momentum is not negligible. So the big symbol in the center is total orbital contribution to angular momentum. The S symbol is total spin angular momentum. And the J symbol here is summation, result of addition of the spin and orbital angular moment. Total angular moment. So as soon as we go away from like hydrogen atom, as soon as we go to heavier atoms that experience influence of environment, as soon as we have many electrons that interact with each other, even in if all of the electrons contributing to the symbol stay on the same ion and take the same value for principal quantum number, they may contribute different energies because of electron-electron interactions. And there are different electronic configurations characterized by these different symbols that will have different energies and different contribution to spectral activity and immediately to the magnetic activity, because magnetic properties are associated with angular momentum. So if we do have several electrons, we need to find these three values and then identify which of them will be the smallest one. And here the 2s plus 1 will be multiplicity, which tells degeneracy of the symbol. I almost started flying and prevented. So if the half-filled shell is known to contain specific number of electrons, they can be distributed over different quantum states in several configurations. And the idea is that by redistributing electrons in different configurations, one can obtain different values of magnetization and different total energies. So if we have shell with orbital quantum number L and we have X electrons, then from combinatorics, from statistics, one can find the number of such configurations. And we are going to look through the stuff on the example of the boron, butyl boron atom. So hydrogen, helium, lithium, what is that? Beryllium, boron. Number 5. Right? And the first S shell and second S shell are completely filled, so we do not care about. So we are only on the second principal quantum number 2 and orbital quantum number equals 1. Right? Equals 1, and we are dealing only with one electron. So if you plug these values into number of microstates, we are going to get 2, 1, 2, so 3 plus 1.
2 plus 1 times 2 is 6.
2 plus 1, 3 times 2, 6. 6 minus 1, 5. So we are going to see the 6 microstates that can be taken, 6 configurations that can be taken by boron atom. And typically one writes different values of the. So we are going to make a table of microstates. So we will explicitly write down distribution of each distribution of electrons over quantum states, but where does it come from? Why do we write this distribution? I don't know. We'll answer it next time together. But probably it is because, no, we just want to enlist all of them. And the benefit of writing this table is to avoid rigorous math and and intuitively make connection from what we can do by hand quickly by scalar addition of arithmetic numbers and vector addition of angular momentum. So by seeing signatures of scalar addition that we will do in the table, we will be able to guess what will be results of addition of angular momentum between electronic and orbital part. So this will guide intuitive addition of angular. So, how many quantum numbers are used in hydrogen atom to specify the state of an electron? Huh?
In hydrogen atom?
Yes.
Forward.
Electron, yes. Which
Oh,
one?
yeah.
So which ones?
Principal. It's M, L, M, L, S.
Principal, secondary,
M, L,
ML, which is angular momentum, and
and
MS.
S.
Okay, so if L equals 1, then ML goes from minus L to plus L. So for P electron, this one, it can take different values of the projection of orbital angular momentum. And here we can guess the total Z projection of orbital and spin angular momentum. So if we do have one electron, we can place it to the state with orbital projection plus 1. Then angular contribution will be plus 1, and magnetic contribution will be plus 1/2. Right? Then we can do the same in place electron spin up in the state with orbital projection equals 0. Then orbital projection 0, spin projection plus 1/2. Then we can put it with different value with -1 orbital projection. And it will be still spin 1/2. And then one can repeat the same pattern for spin down. Orbital projection 1 plus 1, spin projection -1/2. Orbital projection 0, spin projection -1. Orbital projection -1, spin projection -1. But in both, so we do see two sets. But in both sets, if we
if we identify that projection of total angular momentum changes subsequently from -1 to 1, we can tell that the orbital angular momentum for all electrons equal 1 here, but one can do the same table, filling it with several electrons. 1, and we see that total spin projection, not projection, total value of spin is 1/2. And same here, although it takes negative projection, we see that total value of orbital angular momentum is 1, and total value of spin angular momentum is 1/2. I hate it so much. No. It's length of the spin vector.
Oh.
It can be, projection can be up and down, but length of the vector is fixed. So,
Yeah.
few minor steps more. I'm going to erase the previous panel and write the I'll keep this notation and remove the rest. So when we deal with hydrogen or hydrogen-like atoms, we use alphabetical nomenclature for angular momentum. S, P, D, F for L equals 0, 1, 2, 3. But here, although we are doing oversimplified example for poor boron, but we are going to use the same intuitive approach to multi-electron atoms and to systems with much bigger values of angular momentum. So here it is not from one electron, but summation of all electrons that contribute to incomplete shell. And because potentially it is contribution of several electrons, it is a bigger system, capital, uppercase. So for L equals 0, one use S capital. For L equals 1, one use D capital. For L equals 2, one use D capital. For L equals 3, I use F capital. And one uses different alphabetical codes for higher value of total momentum. I just do not want to lie, but they seem to continue alphabetically. J, H, I, G, H, I, J, K. And we may need them later, but we will use some sources. Okay, so based on this table, we can identify that for boron, our L will be encoded with letter P. Okay? The total spin of all electrons contributing to this configuration is 1/2. 2 times 1/2 plus 1 will be equal to 2. And here one can use the same table for 2s plus 1 equals 1.
3. So if one makes this arithmetic conversion from value of spin to spin multiplicity, it tells what is the degeneracy. Like spin 1/2 has 2 possible projections, up and down. 2 means double. If total spin is 0, then just 1 configuration, no degeneracy. So it is only single configuration. If total spin is 1, then there are 3 degeneracies. C is equals 3, so it is triplet. And then one can continue this sequence and recall the exotic names like quartet, quintet, and use verbal language to take into account the higher values of the spin. So we agree that the configuration of the Born will be doublet P, and now we can make vector addition of this orbital and spin angular momentum, which can go constructively or destructively. If it goes constructively, we are getting J equals 1 plus 1/2, 3/2. And if it goes destructively, so at this point, one can quickly recall so-called Hans rules that are established for intuitive. So it is a conversion of equations into human language for intuitive identification of which configuration of multi-electron system will provide the smaller total energy. And if you were exposed to Aufbau principle, it was written here, like 1s2, 2s2, 2p1. One tries to occupy shells one by one, but if there are incomplete shells, first one occupies all values of orbital momentum with the same spin, and then tries to pair spins. So it is consequence of one of the Hans rules, this total number of 3. And the third Hans rule tells that if the values of total spin angular momentum and total orbital angular momentum are equal for 2 configurations, then one needs to select the one with the smallest value of total angular momentum and assign it as the lowest energy. There are ways to derive and get these rules out of rigorous calculations, but I'm not sure if you will do it in our next meeting. So based on third Hans rule, this will be the ground state configuration of Born. Third ground state of Born.
So we did example of microstates, we did Warren example, and we briefly skimmed through Hunt's rule. Let me make, we are about done, but let me make a very quick comment that may establish connection to your computational chemistry interests. Some of you, or maybe all of you, did practice the work with so-called Gaussian software package. And you may have practiced the time-dependent excited state, time-dependent density functional theory, TDDFT. So the keywords for Gaussian software allow to compute excitations of two types, singlet excitations and triplet excitations. Did you hear it? Okay, I see like 2 or 3. Let's see. But as you see from now, there is a much broader variety of spin configurations and angular momentum configurations. Is there a paradox? Why don't we have quintet excitations in the keywords of the Gaussian? Why don't we have doublet excitations? How to convert what we started to cover now with what we see in the keywords of Gaussian?
Doesn't that depend on the number of electrons? And since Gaussian typically is for closed shell systems, if you have a doublet, that means you have an unpaired electron. And it's not an open shell system code, then it would fail.
No. Sometimes things fail, but there are no restrictions to apply, formal restrictions to apply Gaussian to any of those configurations. With triplets, octets, quintets. So the keyword singlet and triplet excitation do not deal with total angular momentum. They deal with change in angular momentum. So if you are exciting your system with keeping spin projection, like you're exciting to this microstate or maybe to another shell, but keeping total projection of spin the same, then it is a singlet excitation. Although we can be in open shell configuration. But if we are making spin flip excitation, we are going from delta S will be plus minus 1, so from this one to this one. Then in simplest cases it would correspond to transition from singlet to triplet, but in more generally it is any spin flip excitation. Excitation with change of the spin projection, and therefore for shorthand notation they are called triplet excitations. But one can apply this triplet excitations to the high angular momentum configurations. Do you want to hear anything more? Let's try to summarize this stuff more rigorously and maybe more rounded up. And please glance through possible subjects for presentations. So they shouldn't be exhausting. It should be something that you can probably connect to your research interests and something that you can prepare maybe in 20 minutes and present in 4 minutes.
Can we choose early?
Huh?
Can we choose early?
You're ready to choose?
Yeah. I want the easy one. No, but also I'm taking organometallics this semester, so I think it's...
So what I suggest we will do next time, I will, although we all have copies, I'll take one copy and make it circle, and everyone writes the name, first choice, second choice, and then I'll quickly look and tell, okay, let's do. So there are more options than students in the class. So probably there will be no conference.
That's why it's called democracy.
Yes.
What?
Democracy.
So we're all gonna vote on which
What
one
one do you want?
chooses?
Yeah, you write your name down. And then we choose. So like you do like one by one, we write two. So if multiple people on one.
So like we're writing our name down and then Russia chooses.
Yeah.
Democracy.
No, I'm not.
Terrible.
Hey, did you forget what Svetlana said?
What?
No,
That's
it's not obvious.
The discussion is so vivid that I better focus camera on you guys. Okay, with this, the meeting number 5 is dismissed. I look forward to see you on Thursday, and we are going off record, but I will stay here and answer questions.
Oh shoot, that comment was on record?
Yeah.
Oh no.
So now Dimitri can tell Svetlana like, oh, do you hear this?
It was a joke.